So far in the course, we have discussed a number of topics, starting from binary arithmetic to basic logic gates and logic functions, logic theorems, codes, and also certain electronic devices like the MOSFET, which make up circuits. Now, armed with this knowledge, it is time for us now to step into the bigger game. The question now is that we are fairly familiar with Boolean theorems. We know how to write truth tables, and we know how, if given any logic expression, how to realize those functions or those expressions using some logic gates. We are aware of that. But the question is there any way in which we can know whether the expression that is given to us is a simplified form or not? Simplified expressions are obviously more preferred as they are easier to handle. So therefore, the question would arise as to how we can know what is, or rather whether this expression that is given to us is the simplified form of the expression or not. So one way to think about this is that there could be n number of logic functions or infinite number of logic functions. Functions could be of 2 variables, 3 variables, 4 variables, and more. So we know that as the number of variables in an expression increases, the truth table also becomes bigger and bigger. Because if there are, let us say, an n number of variables, then the truth table will have 2 raised to n number of rows. So therefore, we have to ask ourselves is there any specific way to proceed? Because of the diversity of this logic functions, logic expressions, it will always be advantageous if we can represent any logic function in a standardized form. And from there on, we can ask ourselves that once we have a standardized form, can we then have a common technique through which we can actually attempt to simplify that function? So let us discuss that. Now, let us start with simple things. Suppose I have some system. I have a system which is fairly straightforward. Let us say there are 2 inputs, A and B. And there is one output, Y. So let us say that we can express this system functionality by means of a truth table. So let's say the truth table looks like this. Suppose now the truth table looks like this. So since it's a 2 variable system, we can just quickly take a look at this truth table and say that okay, this looks very similar to a NAND gate. But suppose we are not very well aware of gates at the moment, and our only question is that just by looking at the truth table, is there any way through which we can obtain a logic expression? So this is the question. Notice that right now we are not asking whether the logic function or the expression that we would like to achieve, whether it will be a simplified form or not. We just want to know, first step is whether we can achieve it. Then the question comes of whether it is simplified or not. So obviously, as you can see, because y is the output, it will be some logic function of a and b. So y will be equal to a function of a and b, some function. Now what that function is, we have to accurately find and identify. So there's a technique to do this. The technique lies by looking at y as the first step. So let us go as the first way. The first way, step 1 is to hunt for ones in y. Look at the y column and start hunting for ones. Now in the y column, where are the ones? We have 3 ones. We have 3 ones over here. And then for those 3 rows, look at what is a and b. Look at a and b. And when you are looking at a and b, you will say that if a is equal to 0, it indicates a bar. And if a equals 1, it indicates no bar. Likewise with b. If b equals 0, it indicates b bar. And if b indicates 1, it is simply b. And the third step is each row corresponds to a product. So step 3 is each row corresponds to a product. Each row corresponds to a product. So therefore, let us rewrite the truth table. So our question of interest is only these 3 rows because they are ones. So we have done the first step. We have identified the ones. Now second step. So first step is this, which we have done. Now let's do the second step. For each row, look at a and b. So here a is 0 and b is 0, which means the expression is a bar, b bar. But what did we say? Rule number 3, each corresponds to a product. Each row corresponds to a product. So therefore it will be a bar dot b bar. This is a bar, this is b. So this row will be a bar dot b. This row is a dot b bar. Now why are we doing this? Why are we doing this? Is because if you notice in each row, if we put this expression, then indeed the y comes out to be a 1. Here a is 1, b is 0. So therefore a dot b bar will give me a 1. There is no other possibility. So we have with this completed step number 3. And step number 4 is all rows will be odd together. So therefore we have 3 product terms. So therefore we can write y as equal to the OR of all of these, that is a bar dot b bar plus a bar dot b plus a dot b bar. This is what we get. Now what we have got over here may not be simplified. Okay, so that is not the question right now, which we said anyway. So essentially, we discussed 4 steps. And 4 steps in the process of hunting for ones. So the first step is to hunt for ones in the Y column. Second step is to look at the row and assign bar or no bar on each variable depending on whether it is 0 or 1. Third step is that each row corresponds to a product term. And the fourth step is that all rows will be ORed together to obtain the final expression for Y. It's not final, but it is some expression. So in this step or in this process, we saw one way through which we can get some expression just by looking at the truth table. Now, you can see something very interesting. Each term is a product, and all the product terms are ORed together. So here it is OR, but it looks like sum. So therefore this form is called as a sum of product form. Or SOP. One more thing to note is that each of the individual term is a function of all the input variables. You will not find a single term here which is dependent on only A or only B. Each of the individual terms is a function of all the input variables. So this form, where each individual term is a function of all the input variables, is also called as a canonical form. So therefore this is called as the canonical SOP form. So we saw one way through which we can get a canonical SOP form for a system just by looking at the truth table. Okay, so now let us ask ourselves, just like the way in which we did this by hunting for ones, can we do this by hunting for zeros? Well, we definitely can. So let us take another example. So let us say I have a system or a truth table where I have A, B and Y. Suppose I now have Y looking like this. So again over here, step 1 is hunt for zeros in Y. So how many zeros are there? These 3. Step 2 is look at the row for each 0. Now over here, if A equals 0, it is the opposite. That means it is no bar. And if A equals 1, this indicates A bar. Likewise, if B equals 0, it is only B. And if B equals 1, then it is B bar. Notice it is just the opposite of the technique we saw where we were hunting for ones. Over there, if A equal to 0, that was A bar. And A equal to 1 was A. Third step is that each row corresponds to a sum, that is an OR term. So therefore, if I do step 2 over here, what will I get? I will get A and B bar. Because here A is 0 and B is 1. And each row corresponds to a sum term. Earlier, For the one case, this corresponded to a product term. So now you see they are duals of each other. Likewise, this will be A bar plus B. And this will be A bar plus B bar. And the fourth step is that all rows will be ANDed together. Just the converse. So therefore, what will we get? Y will be the product of these three. So they will all be related together using a dot. So this is what it looks like. Again, this may not be simplified. This may not be simplified. So something interesting to note over here is that each term is a plus term. Each term is a plus term. Notice over here, although I say the word sum, it is actually OR. It is not addition. So rather I should say plus. I should not use the word sum. But although the word sum will somehow come into picture because it looks like it, but it is actually OR. So therefore, each row is corresponding to a plus term, and each term, as you can see, is just that. And all the terms are combined together using dot or a product. So therefore, this form is called as the opposite of the previous one, or a product of sums form. Also called as POS. That was SOP, this was POS. And each individual term for the row is a function of both variables. Nowhere you will find the bracket containing only A or only B. So again, this is a canonical form. So therefore, combining both of these, this is a canonical POS form. So let us properly define canonical form. Let us properly define what is canonical form. Where each individual term, so canonical form is that where each individual term is a function of all input variables, not a subset. So as we said, where each term, either the product term or the sum term, is a function of all input variables of the system. And second point is that the canonical form need not be the most simplified form. So suppose I have a system where I have three inputs, for example, A, B and C, and an output Y. And I want to represent Y in the Sov form. Then this may be possible. So what you can see in Sov form, each term is a function of, or each product term is a function of all the variables. So therefore this is canonical sort. But if y equals, let us say, ab plus bc plus a bar, b bar, c bar, what we see is that while this term has all the input variables, these two terms are more simplified. So therefore this is non-canonical SOP. Likewise, if y equals a plus b bar plus c dot a bar plus b bar dot c, so plus c dot a plus b plus c bar. Again over here, this is a POS form, a product of sums, and where each sum term, each individual sum term is a function of all of the input variables of the system. So therefore this is a canonical POS. But if y is something like this, a plus b dot b plus c bar dot a plus b bar plus c. These two, as you can see, are now simplified. These individual terms are not functions of all the variables. So therefore this is non-canonical POS. So therefore the knowledge of this kind of representation is very, very important. Canonical is a very standard way of representation which need not be the most simple. Canonical is a very standard way of representation which may not be the most simple. But it certainly provides a uniform playing field to all the possible logic functions. From the canonical form, you can definitely use Boolean theorems to simplify. Okay. So, with this, let us see a little bit more on how we can simplify. Let us now look at 3 variable systems. Suppose I have A, B, C and Y. So the way to write the truth table would not change. There will be now 2 raised to 3, that is 8 rows. Now each row will be numbered from 0 to 7. So convert all the numbers from 0 to 7 in order into their 3-bit binary form. So this is 0, next is 1, then 2, then 3, then 4, then 5, then 6 and then 7. This is how you enter the inputs. Now suppose y looks like this. This is what y looks like. Now suppose we want to write this in the post-canonical form. Then what do? We hunt for zeros. This is a 0, this is a 0, this is a 0, this is a 0. So we found 4 rows. 4 rows where you will see a 0. And each of those rows corresponds to a plus term. So the first term will be A bar plus B bar plus C bar. No. This will not be A bar plus B bar plus C bar. This is a pause. So therefore, 0 means it is no bar. Then this term will be A plus B plus C bar. Next is A plus B bar plus C. Dot this one, that is A bar plus B plus C. This is the canonical pos form. Now, if I want to do the opposite, I want to write the sub-canonical form. What do? I will look for the ones. There are 4 ones. So now, this one will be A bar dot B dot C. This one will be A dot B bar dot C. This will be A dot B dot C bar. Plus finally A dot B dot C. Alright, so we have seen how to get the canonical forms in both pos form and sov form. That is the product of sums and the sum of products form for y. Now both of these are correct and ultimately they will give you the same expression with it in whatever way you simplify. Alright. So that is the way. Now, let us ask ourselves, apart from giving a way to represent in a standardized Boolean algebra form for the logic functions, does this canonical form serve any other purpose? Yes, they do. In fact, they do. If you have a function in pos form, you can represent them using NOR gates only. And if you have a function in sov form, you can represent the function using NAND gates only. Remember that NAND and NOR are universal gates. So therefore, if you have it in sov form or pos form, you can definitely represent that function using only those universal gates, nothing more. So we have this. We have a sov canonical form. Let us see how to represent this using NAND gates. So we have y equals A bar dot B dot C plus A dot B bar dot C and A dot B dot C bar plus A dot B dot C. I think that was it. Yes. So how do you represent this using NAND gates? So each term or each product term corresponds to one NAND gate. So therefore, there are 4 product terms. So we will have 4 NAND gates. And the inputs will be whatever this is, A bar, B and C. Now how A comes from A bar, that is not a concern. You can use one more NAND gate if needed, but that's a separate deal. Then you have A, B bar, C for the second term. For the third term, you have A, B and C bar. Then you have A, B and C. So you have 4 NAND gates corresponding to each product term. Finally, you will have one NAND gate to combine all of these individual outputs. So that is the way. and we have a y over here. Now you may ask, how does this work? How do we know this is working? Well, let's see. If I am combining a bar, b and c, what will be the output over here? It will be a bar dot b dot c, the whole bar. This will be a dot b bar dot c, the whole bar. This will be a dot b dot c bar, whole bar, and this will be a dot b dot c, whole bar. Now, all of these are combined as y. So therefore, what will we get? We will get each individual term. Let me not write it over here. Let me write it separately. So here we will get y equals a bar dot b dot c whole bar, a b bar c whole bar, a b c bar whole bar, and a b c whole bar, and each of them will be ANDed with a whole bar. So if we use De Morgan's theorem, what will we get? We will get a bar b c bar plus a b bar c bar, because these dots will now get converted into pluses. A b c bar plus a b c bar. So the two bars will get cancelled, which will be a bar b c plus a b bar c plus a b c bar plus a b c. What you see is that this and this are the same. So with this, we have learned how to take a canonical Sov form, and convert it into a realization using NAND gates only. Similarly, we can do the same for POS form. Let us see how. So for the same problem, the POS form in canonical was this: a plus b plus c dot a plus b plus c bar dot a plus b bar plus c dot a bar plus b plus c. So once again, each sum term corresponds to one NOR gate. So once again, you will have 4 NOR gates because there are 4 sum terms. So let us say NOR will be like this. This will be A, B and C. This will be A, B and C bar. Once again, we are just assuming that C bar is generated separately. This is A, B bar, C, and this is A bar, B and C. And finally, just like the previous case, one NOR gate to combine all of these. Right? Once again, let us verify this if it works. This will be A plus B plus C whole bar. This will be A plus B plus C bar whole bar. This will be A plus B bar plus C whole bar. This will be A bar plus B plus C whole bar. So therefore, this Y will be a NOR of all of these. So therefore, what you will get for this Y, so Y will be equal to with a whole bar. Once again, using De Morgan's, you will get a plus b plus c bar bar plus a plus b plus c bar 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 plus a plus b bar plus c bar bar. Sorry, this will be dot. Be very careful when using De Morgan's. The pluses will be replaced with dots. So the answer is a plus b plus c dot a plus b plus c bar dot a plus b bar plus c dot a bar plus b plus c, which is the same as the initial expression. So, what have we done? We have seen how to represent a canonical Sov form using NAND gates only and a canonical POS form using NOR gates only. This is our first step that we have completed, which will help us correlate a truth table with an expression which we can realize using gates. Okay, so earlier, towards the beginning of the course, when a big looking function would be given to us, the realization using universal gates would not be so simple. The realization using universal gates would not be so simple. But now that we have a technique where we can extract the realization from the canonical forms, where we see that each individual term corresponds to a gate and one final gate you will need to combine the other terms, whether it is NAND or NOR. That is the case. Of course, the number of gates in the NAND case and the NOR gate case may be different. In this particular example, we saw that both POS and SOP forms give you realizations using 5 gates, but that need not always be the case. There may be a case where you may need more number of NAND gates. There may be a case where you may need more number of NOR gates as compared to the other, but that is not a major issue. Now, with this, let us take a little bit more look at the truth tables and the two techniques which we discussed towards the beginning of this lecture. The first technique was to hunt for ones and the second technique was to hunt for zeros. Suppose we have a simple 2 variable truth table. And y looks like this. So, when we look at the technique where we are hunting for ones, essentially we get these two other rows. So from here we get product terms and finally we end up with the sub form. So corresponding to this one, this term would be a bar dot b, whereas corresponding to this one, this term would be a dot b bar. Now, each of these terms has a very special name. They are not just product terms only. They are called as min terms. M-I-N-T-E-R-M-S, min terms. Now, suppose we do the same thing but hunting for zeros. Same function. Now we are looking for this. So ultimately we will get a pos form. So corresponding to this 0, this term would be a plus b, and this term corresponding to this 0 would be a bar plus b bar. Just like the earlier case, these two terms also have a name, and that is called as max terms. They are called as max terms. So the terms where you look for ones in the truth table output, those terms are called as min terms. And the terms where you are looking for zeros in the truth table output, that is called as a max term. So you may question why that is. You may question why that is. So the reason is not very difficult. What you are seeing, each min term is the product term, and product means it is and a product is more likely to give you a 0 than a 1. Therefore the name min term. In the AND truth table you have 3 zeros and 1 1. Whereas if you look at these are OR terms, and OR is more likely to give you a 1, because in the truth table there are 3 ones and 1 0. That's why they are called as max terms. But the irony is, min terms we are actually looking for ones, and max terms we are actually looking for zeros. So let us discuss this in the purview of a 3 variable function, the same one which we had taken a look at just a little while back. Now I am going to keep one more column over here, it's called as number. This number is nothing but the row number. So there are 8 rows from 0 to 7. So likewise you can fill the truth table. So now suppose we want to write the canonical pos or Sov form, we can do that. So let us write the canonical Sov form, or let us say, yeah, but using min terms. So if I want to write in Sov form, I have to look for ones. So the min terms are this, and this. That is row number 3, 5, 6 and 7. So the min terms are 3, 5, 6 and 7. So one more way to write this as y equals function of a, b and c. Because it is Sov, we will see it as a sum of min terms, because each min term corresponds to a product term. So therefore we are writing the min terms and adding them using this summation. Now if I want to write the canonical pos form, so I have to now look for zeros, this one, this one, this one and this one. So these are the max terms. A small m indicates a min term. The max terms are 0, 1, 2 and 4. So once again I can write y equals the function of a, b and c. Now that is equal to the product. Now product, just like sigma, is expressed using capital pi. This is product of max terms, where max term is indicated by a capital M of 0, 1, 2, and 4. Notice that in the brackets, the terms are different. A single term cannot be both max term and a midterm. Okay, so this is a more condensed way of representing canonical forms. Rather than writing those big expressions, big brackets, and so on. So these are some algebraic ways through which we can represent the canonical forms. We shall continue from this point, this very point in fact, in the next lecture. Thank you.